and resultant arc length. Okay? So, real quick, same thing. Let's start here. Excessive speed. The welding machine cannot put out enough current to melt the wire fast enough. So, your voltage and your amperage are going to run there. What happens is you start getting that hesitation. It's poking and bouncing off. Okay? And it's stabbing it, and you're pushing your hand back while you're doing that. So that means your wire feed speed's too high. Slow it down. Okay? So you might be 230 inches per minute. You might need to back it down to like 200 to start with, or 215. Okay? If you still feel it kind of pushing away, and say it's taken a while to get there, back it off a little bit more. Or possibly take your voltage up a little bit more. Okay? Your voltage and your wire speed need to be fairly comparable. They're kind of like going up a ladder, okay, or like carrying two buckets of water, okay, on a scale. If one gets heavy, it's going to tip the other one. They have to be fairly comparable. They don't have to be the exact same, but they have to be fairly comparable going up. If one's way higher than the other one, this is going to be all the way down on this end. You're going to dump your water, so forth. Okay? So, back to this. Excessive means it's just going to be burning out. There's not enough amperage there to do this. Okay? A decrease in wire speed results in less electrode being melted and possible burnbacks. So what does that mean? That means if your wire speed is too low, here's what happens. It'll catch, and then it'll burn all the way back to the tip, and then it'll come out and burn all the way back to the tip. Now this happens really, really fast. You're not going to watch the whole thing burn back out, but sometimes this will happen if you get too far away too. It'll load up with voltage and amperage, it'll burn, and then come back towards the tip. So if that's the case, and you'll see this quite often, turn it up just a little bit on your wire speed. Now everybody used to say, a lot of people say that amperages, your wire speed's your amperage. Not always. Okay? You go off of inches per minute, you go off your wire speed. Then what happens is the amperage will go with it. It also depends on the amount of resistance that's there, what type of material you're welding with. So the more, if you're running 30 inches per minute more, your current or your amperage is going to drop quite a bit. The one thing we're trying to maintain is the voltage. So the amperage is the one that fluctuates up and down. Okay? When we're talking about wire speed, we want to be thinking about inches per minute or millimeters per minute or whatever we're looking at. Okay? It's not directly related to the amperage. The resistance and everything else makes a big, an essential variable in there that can make it sway quite a bit up and down. Okay. Alright, so here we go. Correct, nice molten. Excessive, I've never seen that happen. But usually you'll know what this means by the time you do it. And everybody does it a few times. Back it down, let it burn off correctly the way it's supposed to. Okay? So the chart in table 22-2 on page 735, recommended variable adjustments for the GMAW as well. This is a really good chart. Explains what happens when your welding variables change. Okay? Go ahead and feel free to read through this. So real quick, if you're going to maintain a given amperage and switch from solid wire to metal cord wire, either jump one wire diameter size and keep wire feed speed the same, or keep the same wire size and increase the wire feed speed. So real quick, we're cross-sectional dimensions, so this is a solid wire. Say this one's a hollow cord wire. So our cross-sectional diameter within the wire is different, okay? So basically, instead of one big solid piece of 3-inch bar versus a piece of 3-inch tubing, correct? There's less surface area, less material there, even though the outside diameter is fairly comparable. It's going to take less amperage. Excuse me. Each type and size of electrode has a minimum, maximum current density. Here's table 22.3, which is on page 736, gives you parameters, comparative current ranges and other parameters for carbon steel, stainless steel, and aluminum. Okay. So, for example, increase in current will increase bead height and width. Voltage must also be increased. Too high, possibility of electrode burn back into the tube, arc unstable, gas shielding is disturbed, and usually a lot of spatter. Too low a current, it's unstable arc, not as good a fusion, electrode becomes red hot, arc may be extinguished, less penetration. Start getting burned back and so forth. Travel speed. Travel speed and technique are by far the two most important things to worry about when we deal with wire, okay? Do not outrun your puddle, and then that's pretty much any welding, okay? Do not outrun your weld puddle to where you're walking away from it, because then you're not going to get nearly as nice of a weld bead. But if you just sit there and let it build up, then you're not getting as good a fusion into the base metal either, okay? So, too slow, unusual weld buildup, too fast, and you're not going to have a very nice weld bead appearance, okay? If increased, necessary to increase wire feed speed, which increases current and the burn-off rate, okay? Right here. Must be at the leading edge of the weld pool to assure penetration and fusion. See right here, it's the same thing. Make sure it's at the beginning of the leading edge of the puddle. So here's a chart just showing optimal travel speed. If you go too slow, it's shallow because you end up building up more. However, right in the middle, you've got really good penetration, but if you go too fast, it's the same thing. You're back down to a shallow. Okay. Here's a summary of operating variables. I want you to read these on your own. Make sure you're aware of those and the variables that can affect gas metal arc welding. Weld defects for gas metal arc welding. They're very similar to other courses, other than with a few exceptions. For example, do we have slag on gas metal arc welding? No, we do not. So we're not going to see a lot of slag inclusions in there. Incomplete penetration and fusion are usually the two main ones. All right. Incomplete penetration result of too little heat input into the weld area. Correct by increasing wire feed speed and reducing electrode extension. Excessive penetration is usually causes excessive melt through, really heavy icicles on the back. Back your voltage off, your wire speed off, maybe increase your travel speed, things like that. Okay. Too much heat into the weld area, which also can cause distortion as well. Another cause is improper joint design. Okay, and this is improper joint design can be for excessive. It can also be for incomplete penetration as well. If you're trying to do a square groove weld on a piece of metal that's just it's too thick to do it in one pass, you need to make sure to grind it back and prep it correctly. Okay, open it up to where you can get a good joint penetration to the back side, even if you have to do like a If it's 1/4 inch and you got to grind it back down and do it in 3 passes versus 2, that's a lot better pattern and getting good penetration and good fusion along the entire weld, okay? Whiskers. Whiskers are little stubs that go through, and you'll see this from time to time, especially when you're doing an open or up weld. Code says they have to be minimal, okay? Doesn't necessarily say you're allowed 1, you're allowed 2, you're allowed 3 within anything. I'll tell you right now, I don't allow any, none whatsoever, okay? Most inspectors I know will not allow any whatsoever as well, all right? And sometimes everything can be right when you're doing this as well. When it doesn't always have to be something wrong with the machine, it can just be you. It can be your travel speed or just a little mistake. If you notice that it happened, stop, grind it out, start back into the weld again, okay? It's important that if you notice that it shot through and then it's stuck, that's when you want to stop, grind that piece out, fix it before you go any further, especially on an open run. Voids, some of them are referred to as wagon tracks because of the resemblance of radiographs and the ruts or the dirt. Wagon tracks are usually right here and right here because of this high crown. And then a lack of penetration or fusion in this weld joint. So usually what happens is it crowns like this, and then you come in, you'll knock that off, and you'll put a weld pattern in here. Well, then we see with the weld going down this entire distance. See it here and here, just like a set of old wagon tracks going down the road, okay? The lack of fusion right here and there. Incomplete fusion, also referred to as overlap. The AWS defines overlap a little different. I think we've talked about overlap before. If not, overlap is usually a result of incomplete fusion, okay? So overlap is when your weld puddle comes over and exceeds 90 degrees, okay? Right here, this is a lack of fusion. Right here, incomplete fusion. It didn't fuse all the way to the base metal. It may even be more drastic like this as well. Okay, if it exceeds 90 degrees, that is considered a lack of fusion. However, a lack of fusion can also be just as in here. Lack of fusion here, lack of fusion here. It doesn't have to extend beyond 90 degrees as well. Okay. Porosity. Porosity is one of the biggest ones with gas metal arc welding because it's got an external shielding gas and not a slag or not a flux. Usually it's a little bit of air, so forth. The atmospheric qualities or the elements, the outside elements can change and blow your gas shielding or your shielding gas away from the weld puddle. therefore creating porosity. It can also be from within the base metal. Say if you don't have an open root, you're trying to weld a root on the bottom of the table. So, say you're doing an open root weld, and right below you is the bottom of a table. Your gas is going through the root and bouncing right back up at you, so you're fighting yourself. Think about that when you're doing that. A lot of times people in the booth will want to go in, they'll set it together, put it right on top of the table, try to weld it up. Well, your gas is shielding right back up in, creating more porosity in the weld. Make sure it's off the table so your gas is shooting through the root, through the backside of the weld, and not causing you any harm as you're welding this piece of material. Okay? Speed can be too fast as well. If you're out running your shielding gas, for sure. Shielding flow gas rate can be low. It can be too high. Must be a welding grade gas. There can be pinholes within your systems. The O-rings on your guns tied in at the machine side. Everything else. Look at the bottom, the form material, oil, dirt, rust, grease, and paint are huge portions of porosity within your weld. A lot of people don't want to clean it off. They think they can weld back over it, and it's got some paint on it. Usually that ends up burning off or getting a bubble, so it creates porosity within the weld. Okay, other defects. Warpage. It occurs when forces of expansion and contraction poorly controlled. Most of us know what warpage or distortion is. Okay. Spatter. Made up of very fine particles of metal, usually caused by high current, long arc, irregular and unstable arc, the improper gas, improper work or travel angle, or clogged nozzle. Usually clogged nozzle, and 90% of the time it's either your current is too high or your wire speed's too high, and you're staying too far away from the material itself. Okay? A lot of welding machines get blamed for spatter when it's technically the welder that needs to change their needs to change it up a little bit, and or even their technique to reduce the spatter as well. Weld cracking, go ahead and read through this. A regular weld shape. Undercutting, cutting away at the base metal along the toes of the weld and not filling them in. Okay? Most of us know what undercutting is at this point. Usually high heat can contribute to this, along with welding position, poor technique. To correct, usually there's some manipulations in there. Slow your weld speed down or drop your heat down a little bit, your voltage or your amperage, whichever process you're running. A lot of it can be maintained by proper rod angle and manipulation. Clothing regulations. I'm not going to read this. If you've been through this, you've been through handling of gas cylinders. We've talked about ventilation. Feel free to read through this on your own as well. Wire feeder safety. Okay, so wire feeders, you can run the amperage through the wire, will go through the wire feeder itself from the welding machine as you're welding. So, make sure to turn the power off when aligning and adjusting drive rolls. However, most of the time, we do not do this. Most of the time, it's not an issue. It's probably a good practice, but for the majority of the time, we're not going to do a lockout tag out on this. Okay? They may want you to. More than likely, you're going to see me do this, and I'm not going to shut the machine off, because what I'm going to do is I'm going to use the drive rollers to help me push it through. But I have to be very careful, make sure that my fingers are out of it before I engage on the button or use the wire jog button or the gun button, either side, okay? We've talked about the knurled versus smooth wire rollers before, the liners. The biggest thing on this is you have to be careful, especially when you're running a multi-process machine like our Shopmates. Whether the contact voltage, the output is on or off, okay? So especially when you're welding around like in our bench, if a piece of metal were to come across and lay between the ground or the workbench and your roll of wire, it can start welding and making a short circuit there. You want to make sure that your output is always regulated off of your gun, and that you usually have some sort of a shielding on the back side of your wire as well, so that nothing can fall on it and short it out, okay? This is the one that I think causes more problems than anything right here, believe it or not. Is a lot of times you'll get porosity or something within your weld. You look at the tube, nothing. You stick it up to your ear and you hit it so you can see if you can hear the gas. And then it pokes or burns you in the ear. And whenever you do that, make sure that you put the gun this direction. I'm not saying you can't listen to it, but to hear it, make sure it's going away from you. Okay? Not pointed into your ear to where it could burn or severely damage your ear or your face. Fire safety, we've been through this. Hot work. Care of the nozzles. Keep them clean every time. After you're done welding, check it. You don't have to do it every single one, but quite often you will. Okay? You can use a screwdriver, use the whelpers to keep them clean. You can use some spatter spray. We don't use it here because we don't need it. Again, if you learn how to control it without it, then you can get out there and start buying your own spatter spray, and it makes life a little bit easier sometimes. But for the most part, you should be learning to evaluate and weld without using aids like the spatter spray or the nozzle gel, okay? I want you to learn how to do it without using the nozzle gel or the spatter spray. Okay, contact tubes. Wire wears the hole to an oval shape. Some of the liners and so forth, contact tubes. This is contact tubes itself. We've talked about this. You'll start losing voltage. It's considered a consumable item. Make sure that there's not a large gap in between the wire and the contact tube itself or the contact tip. Birds nesting. Most of us have seen a bird's nest when it gets caught a little bit out of alignment on the rollers, and it'll start working its way out. Hopefully at some point in here I went through how to load wire, restart it, and everything else with you, okay? We've talked about arc weld in the first beginning courses. I'm not going to talk about it too much more in here. Feel free to look through this on your own.